Okay, so the limit of a function. Last time we talked about just different kinds of functions and how we can kind of tell what the function is doing over the course of a certain domain. You know, is it increasing or decreasing? How is it increasing? How is it decreasing? Well, the limit of a function, we're just going to try to find what the function is approaching, right? So what is the function approaching? And so sometimes, you know, we have clear limits. If, for instance, we have a cup of coffee and it's cooling toward a certain temperature, right? So the graph could look something like this, and maybe it's cooling toward room temperature, and room temperature is 70 degrees. So all I know about this function is that the limit of it is going to be 70 degrees. But that is over here, way over here. So would I say the limit is 70 degrees just anywhere? No, not necessarily. And so what we're going to do is look at specific places of the graph, but one may be more interesting than another, right? I mean, this is definitely something I'd like to know is happening to the temperature of my cup of coffee. So something that has been calculated at some point, you probably knew that the number pi hasn't always been known, right? It just hasn't always been known that it's about 3.14. That thousands of years ago, they just tried to approximate the number pi and using different methods. But there's one method Archimedes used to approximate pi using inscribed and circumscribed polygons for a circle. Okay, so you can imagine. So let's see, I think I have this demonstration I'll try to pull up and see what happens as the number of polygons increases. Okay, so we have okay, here's our circle. You can kind of see that outline. And then here, the area of this inscribed polygon is shown. And right now, the area is about 2.7. But let's try to make the area closer to the area of the circle, right? And to do that, we would increase the number of sides. You see what's happening? So all of a sudden, the area is 3. Okay, I keep going. And the area is 3.04 approximately. And I keep going and going, and you see this graph is being made that the area is converging or approaching the number pi, right? And, you know, the area of a circle is pi r squared. And so if we're talking about a circle with a radius of 1, that it's going to be exactly equal pi, right? The area of the circle is exactly equal to pi. But did we know that a long, long time ago? No. I mean, there were approximations like in the Bible. I think it's approximately just 3. Another approximation is 22/7. Okay, and pi is not equal to 22/7, but it's approximately equal because it's a close decimal approximation, okay? Okay, so the informal definition of a limit. If f of x becomes arbitrarily close to a number L, as x approaches c from either side, then the limit of f of x as x approaches c is L. Okay, it's still a little confusing, but why don't we go back to the graph that we have of the temperature of the cup of coffee. And so we'll try to write this as a statement, a mathematical statement. I would say if this is our function f of x, and this temperature that the function is approaching is your L. Good? Okay. So I could say then the limit, Lim, the limit, as we go in this direction, as we get farther right. So we're going to not talk about limits at infinity today, but I'm just going to write it here. Because, you know, if I go really, really far to the right, my x values are approaching infinity. So the limit as x approaches infinity of the function of f of x is equal to 70, okay? Or that's our limit, L. This is the kind of statement that we want to write. You know, it's not always going to look like this. So let's take a look at this graph that's given and see if we can come up with a statement. Okay. So all together, this statement mathematically would look like this. The limit, Lim, of a function, f of x, as x approaches some number, as x approaches c, okay, is equal to this limit, L. So is equal to this y value. Is that okay? That's a y value. Okay. So in this graph, we can see that I have a labeled point. Here it is. And I want to look to the right of 2 and to the left. Like I want to look in both directions or going inward. Towards 2. So I want to know what the y values are approaching as x approaches 2. Can you tell? What are the y values approaching as x approaches 2?
11.
They are approaching 11. It is. And so I go up here. Here's my 11. And that's kind of a nice limit. It's clearly marked. However, just because if this point were not solid, like if this point did not exist, okay. So say that there was a removable discontinuity here at this point. I'd still say the limit is 11. Okay. Now, why am I going to say that? It's because if f of x becomes arbitrarily close to a number, does it say it reaches that number? It doesn't say it has to equal that number, does it? As x approaches c from either side. Okay, so I can write a statement for this particular example that the limit of f of x, and we can even write the formula in if we would like, as x approaches 2 is equal to 11. Okay, now something else that we may be concerned about are left and right-hand-sided limits. Okay, so in this case, I could write them individually. And so let's do that just to make sure that we know that these are some statements that are valid. Okay, so same diagram, I could say the limit of f of x as x approaches 2, and I know in pre-calculus we use this notation some, but when you have the plus or the minus afterwards, that would tell you which direction you are coming from. So the minus would be from the left. Okay, so as x approaches 2 from the left is equal to, hey, so if I come in this direction from the left, I see that the y's coming in this direction, they're still approaching 11. So is equal to 11. And then one other statement, the limit of f of x as x approaches 2, and then with a little plus after it. So that would be from the right-hand side. So now we're going to come in this way. And we see what's happening to those function values. Do you see how they're decreasing? Okay, so if I'm looking in this way, they're going down, but what they are still approaching is the same number, which is the limit value of 11. Okay, now altogether, in order for a limit to exist, you probably heard the limit does not exist, right? Okay, in order for a limit to exist, these need to match one another. Okay, and they do. And so we're going to say, yeah, what's the limit? The limit of f of x as x approaches 2 is just 11.
What do you write if it doesn't exist?
Typically, we'll write D and E for does not exist.
Okay.
That's right, but now you may still be asked to find a left or right-hand sided limit. Okay, and that's fine. Go ahead and answer those questions. But overall, D and E.
Yeah.
Okay. Okay, so what we can do other than graphically is to estimate a limit numerically, and all this is taking is the same function, the same graph, which was a function y equals, or f of x equals 3x plus 5. Okay, and you can see as I'm coming from which side, the left or the right side, if 2, at first, what am I coming from if 2 is right here? Okay, coming from the left at first, right? And we see that as x is approaching 2 from the left, 3x plus 5 is approaching 11. Got it? So does that make sense? 10.4, 10.7, 10.85, 10.997. So the closer you get to this x value, this is your, as x approaches c, so this must be your c. The closer you get to your c value, the closer your function value should be to the actual limit. But you could also approach from the right-hand side, and you see that these match. From the right-hand side, I could do something like 2.001, 2.00001, etc. And the closer I get to 2, the closer my function value should be to the limit. And in this case, it's 11. Okay, so another notation, another way to write this answer, we could have said the limit, not of just f of x, but put the formula in, 3x plus 5 as x approaches 2 is equal to 11. Hey, but isn't that nice? I mean, when it's linear, quadratic, cubic, There's nothing strange happening to this graph. It's not a rational function. So isn't it nice that whatever the limit is a function value? Isn't that nice? Okay, that doesn't happen all the time. But it is nice when that does happen. And so think those polynomials, that's a good thing to have, a polynomial function. And then you can just evaluate it. Okay? Okay, well, let's try a few. We're going to investigate the value of each of these limits. And I don't know how we're going to do this. We may do this numerically. We may do it graphically. Okay, we'll see what we can come up with. Okay, so at first, this first one, the limit of x minus 4 over x minus 1 as x approaches 2. Okay, so what is the limit of this function? Okay, any ideas?
Instead of x, we have 2?
You could possibly use direct substitution. That's a possibility. Let's try it. Okay, so 2 minus 4, okay, I'm just plugging 2 in, over 2 minus 1. Okay, so negative 2 over 1, so just negative 2. Okay, I think that is it. Now, are we just going to settle on this answer and just say this will always work out so nicely? It's not always going to work out this nicely, so why don't we verify it numerically using a table of values too? Okay, so we'll just say this we think is negative 2. Okay. So a table. We are choosing values of x that are near 2. Okay, so 1.9, 1.99, 1.999, etc. But also from the other side, this would be from the left-hand side. So from the right-hand side, we could have 2.01 or 2.001, right? 2.01, etc. So you're trying to get as close to 2 as possible. And now we plug those values in our calculator and evaluate. Now, I think last time I showed you if you're using a table over and over again, you know, how to evaluate those, the function on your calculator. This is possibly a good time to do that. So I'm going to go to my calculator, type in this function, okay, and so it was x minus 4 divided by x minus 1. Okay, and then I'm going to go to the table setup, which is under Window. The table setup, I'm going to have it instead of independent, which is being auto, which is really, it's just going to give you a whole list of points that are on the graph. I'm going to set it to ask, and then go to the table. Okay, and so what this will show is just nothing, probably. But here's where I can type any x value in, and it will tell me the corresponding y value. So the first one, 1.9, I think it was, 1.99, 1.999. Good. Okay, then going from the other direction, 2.001. Okay, and I know I'm going kind of backwards, but 2.01, 2.1, but do you see from down to up, it's definitely approaching -2. So from either direction, the y values are approaching -2. Okay. Okay, so we verified it numerically. So we'll just write down a couple of these. -2.3. Okay, and 1.99, -2.03. And then 2.001, -1.997. And then 2.01. Okay. Well, one other thing, let's look at our graph. Because we just entered this into our calculator, so I'm going to go back to my graph. I'm going to just type Zoom 6, the standard viewing window, and I knew it was a rational function. I knew it should have an asymptote, which it does, a horizontal and a vertical asymptote. But what I was concerned about is what is happening near x is equal to 2. Okay, so I can do the trace. And then I'm going to kind of jump down. I want to kind of get on the other piece. So let me keep hitting the right arrow. Okay, so if you see, we are close to x equals 2, and the y value is semi-close to y equals -2. Okay, any questions? Good. Okay, this next one. We want to know the limit as x approaches 2 of x squared minus 4 over x squared plus x minus 6. Okay. What happens if I just try to plug 2 in right now?
It's going to be 0.
0, right? 0 over, is the denominator 0 as well?
Yes.
0,
It's
right?
going to be
And yeah, so this would be called indeterminate form, but again, that doesn't tell us, indeterminate form doesn't tell us what our outcome is. So I'm not going to say it does not exist. Okay, it's tempting to want to say that, but there could be a limit that is a real number, and we want to still find it. So another option, we are going to talk about the limit laws in just a few minutes. But for right now, if you're still trying to consider what is happening around x equals 2, let's just try to make another table. And then maybe we'll do a little bit of algebra. Okay, so I would choose 1.9, 1.99, etc. Okay, and from the other direction, let's make this 2.1, 2.01, 2.001. Okay, so trying to lean toward 2. Okay, and because of the complexity, you know, if I wanted to type this in every time, it could take a little while. So instead, I'm just going to use the calculator. So x squared minus 4 divided by x squared plus x minus 6. Okay, and if you go to your table, I'm still going to enter these values in individually. I'm just deleting out my last ones. But if you just want to start under the other coordinates that you had, that's fine. But let's see, type of 1.9, 1.99, 1.999. Okay, and look at this. Okay, it looks like it's 0.8, but is it really?
No.
No. I'm going to hover over the y coordinates because it just rounded, it looks like. So that there's really a lot of digits, and this isn't exactly 0.8. Okay, but let's try from the other side. So 2.1, 2.01, 2.001. Again, it shows 0.8, but it's really not. So you can probably imagine both sides are heading toward a y coordinate of 0.8. Is that fine? Okay. I don't know if that's cheating, but I did it anyway. So, okay. Then this last one, we're going to find the limit. So let's put equals 0.8 because I need to answer the question. But this last one, we want to find the limit of x over the absolute value of x as x approaches 0. Again, if I try to use direct substitution, I see that I get 0 over 0, or indeterminate form. So that doesn't help us. What we could do, look at the table, look at a graph. Okay, one of those. Look at our table, look at a graph. Let's start with a graph for this one. Okay, so x divided by, absolute value is located under the math button, and over to number, and it's the first option. Okay, so here it is, x divided by the absolute value of x. And we'll hit graph and see what appears. Okay, interesting. This looks like a piecewise function, does it not? And from the left, this left piece is approaching a certain y value, and from the right, it's approaching a certain y value. But do they match? They don't match, do they? Right? Because where are we looking specifically? Around what? X equals... We're looking around x equals 0, right? So I look from the left, I look from the right. I can write individual left or right-hand sided limits down, which we will, but together we would say the limit does not exist. Is that okay? And then you can go to the table if you're interested. What if I go back to my table setup and change it, maybe to start at -1, but increase in the table, this is the delta table, this is what your x increases by every time, maybe I just say 0.1, and then change this to auto. And now you can see, look, -1, -1, all those y values are exactly the same. And then same thing for the right-hand side. All of those are exactly the same, but they don't match. Okay? Okay, so we will say the limit of x over the absolute value of x as x approaches 0 from the left, a little minus, is equal to, it was -1, is that correct? It was the lower region. Okay, and then we can say the limit as x over the absolute value of x as x approaches 0 from the right is +1. And these do not match, and therefore the limit, overall limit, does not exist.
I think you'd be able to say the absolute value of
Say it again.
You'd think that the answer would be like absolute value of 1.
Mm-hmm. Yeah, I mean, because we see these are opposites of one another, but we want a clear, like, one answer every time, one particular real number, if possible. And so, because they don't match, even if they are opposites of one another, we'll just say does not exist. Okay, so one other thing for this section is to look at a given graph and be able to tell what some limits are. And so I made this sketch. It's just a kind of complicated piecewise defined function. In the first one, we want to know the limit of f of x is this whole thing, as x approaches -2. Okay, so let's kind of draw where we're looking. -2. Okay. So we look from the left. We look from the right. What are the y values approaching? -1. Now, is this limit the function value at x equals -2? Is the limit the same as the function value there? It's not, is it? Because look, the function value is actually -2. I'm not concerned about this point. I'm concerned still about what the function is approaching on the left and on the right-hand side of x equals -2. And so we're definitely going to say -1. Does that make sense? Okay. The limit of f of x as x approaches 0. Okay, so we're looking around 0. And what are the y values approaching? So from both sides, -3. That is right. And that's easy. I mean, it is the function value. It's the same, but that can happen. That's fine. Equals -3. Okay, one other. What about the limit of f of x as x approaches 3? So 3 is here. Okay, so the left-hand side approaches -6, right? The right-hand side approaches -1, and those are not equal to one another. You see this gap in the graph, right? So if you have that kind of gap, you can find the one-sided limits, but not total. Okay, so we're going to say does not exist. Okay, any questions? Okay. Well, we have one other section to take a look at today. So section 2.3. in this section is on the limit laws. Okay, we have some that are pretty straightforward, and then some maybe a little bit more complicated, and so I will try to get to as many as we can. Okay, so for the first, it says for any real number A and any constant C, the limit of x as x approaches A, it is A, and the limit of C as x approaches A is C. Okay, so let's see why this is true. And to do that, I like to think of what the graphs of these functions look like. Okay, so for this first one, okay, so this particular function is y equals x, okay, which is a line that has a slope of 1. It would pass through the origin, right? So this line, y equals x. And so what we're saying is, as x approaches A, why don't we say here's A? That the limit is also A. The limit as x approaches A is A. Does that make sense? Because your x and your y are equal to one another. Okay, so here is a point on the graph, and it is also at A. Okay, so not bad, but just note, you just plug A in, and your outcome is A. The second one, though, is a constant. And a constant function is always the same, right? And so it's a horizontal line. Okay, so here is this constant, C. So that would be the equation y equals C. And wherever A is, I'll say A is here, from either side of A, the y values are approaching C. They really equal C, but the y values converge to C. Okay, so some examples. What is the limit of x as x approaches 4? Number 1.
Oh, as x approaches 4.
Uh-huh. The limit of x as x approaches 4.
4.
Just 4, that is. Because in this case, think you plug it in. Okay, so that answer is 4. Now, the limit of 10 as x approaches 4. What is that one? 10, right? Because the y value is always 10, wherever you look on that line. Okay, good.
It stays the same, right?
Stays the same. Yep. It's going to be a little bit more complicated. You're right, but we need these basics to move forward with some of those other properties. Okay. Okay, now these next ones. I went ahead and printed them out because I knew that's a lot of writing. And we had a lot to talk about today. So here we go. Okay, so just like we can add functions together, everybody's fine with that, right? Like, I like to think of basic ones, like y equals x squared, and like, y equals 5. So if I added them together, I'd get this new function, y equals x squared plus 5. And what does that do to the graph of the original y equals x squared?
It moves it to 5.
Moves it up, doesn't it? So if it moves it up, what are those y values now? They're bigger than what they once were, aren't they? So how do you think that affects the limit? It makes that different too. So isn't that, so you think about what are some things that I know are true already, and we're just going to kind of put them into some limit laws. Okay, so let f of x and g of x be defined for all x not equal to a over some open interval containing a. Assume that L and M are real numbers, okay, and the limit of f of x as x approaches a is L, and the limit of g of x as x approaches a is M. Okay, so two limits are given for two particular functions, but these x values are approaching the same one, in this case a. So the first thing that we can say is the limit, the sum law, is that the limit of the sum of two functions, like this, f of x plus g of x, is equal to the sum of their limits, right? So instead of you just breaking it up. But why don't we just take a look at those easy functions and kind of write it in so you hopefully have a better understanding of why this is true. But this is no proof by any means, okay? So we said, so for this first one, if, okay, let f of x equal x squared, and let g of x equal 5. Okay, and why don't we say we're trying to find the limit of x squared plus 5 as x approaches 2.
Is that x squared plus q?
Yeah, sorry, it's a plus. It's a plus. Now, my first one is an and. Sorry. Yeah, okay, my ands and my pluses, they look kind of alike. Let me try to make it look better. Okay, and, okay, I don't know if that looks better, but and g of x. And what I've just done is to add those two together. Good. So what we're trying to show is that this, I'm going to put a little question mark, is equal to the limit of x squared as x approaches 2 plus the limit of 5 as x approaches 2. That's our goal. Okay. Now, there's more, this may be a tad bit more complicated than I had hoped. You know, I really want to look basic. Just as simple as I can, but I think we can do this, right? Because this is a polynomial, and we'll see how polynomials, I can just substitute it in whatever value is, or a is. And so the limit of x squared plus 5 is 2 squared plus 5, so 9. Okay, so this limit is definitely 9. Well, the sum of these two limits, okay, so the limit of x squared is 2 squared, so that's 4. The limit of 5 is 5, isn't it? Because that's a constant. So 4 plus 5, and those are equal to one another. And so that just shows in a simple example how those two expressions are equal to one another. Okay, same thing for subtraction. So the sum and the difference laws are very similar to one another. The constant multiple law. What it says is we can multiply a function by a constant. Okay, so like a 5. And what that is, the limit of that new function is the same thing as if you had just multiplied that constant by the limit of the original function as x approaches a, or c times l. Okay, so the limit of c times f of x as x approaches a is equal to c times the limit of f of x. You can factor the c out, or c times l, the limit. Okay, so that's what it says, but let's take a look at a numerical example. Okay, so again, if I have a 5x, or f of x equals x squared, and g of x equals 5, and this time I want to multiply them together, I have the limit of 5x squared. 5x squared is my new function as x approaches 2. And what we're trying to show is that it is equal to 5 times the limit of x squared as x approaches 2. Good? Okay, so let's plug this in. 2 squared, so that's 4 times 5, so 20. 20 is equal to, I don't know, 5 times 4, right? 5 times 4, and those are equal to one another. And so yes, the easy thing to do is factor the 5 out. Okay, we can definitely do that, and we get an equivalent limit. Okay, well, that's the constant multiple law. I'll just let you look at the product and the quotient laws, but do similar things, right? Think about working with more than one function and what are mathematical operations we can do with those multiple functions. What can we do with them? So we could multiply them like the product law. We could divide them like the quotient law. And pretty much you can multiply or divide their corresponding individual limits. Okay, so take one function at a time instead of taking them both collectively. Okay. And last couple, the power law. Okay, so the power law is pretty much what I was doing with my x squared function. I was using it, but let's see how it works. If f of x is equal to x squared, what this is saying is I could instead, if f of x is squared, I could write it as the limit of x squared as x approaches 2. That's one option. But another option is to rewrite it as the limit of x and square that, square the entire limit. Okay, and let's see if those are equivalent to one another. Okay, so this is our question. The limit of x squared. Okay, we said that was really 2 squared, or just 4. And this is the limit of x, so that 2, I'm going to put in this blank. So that's 2. And then square that, which is also 4. And so those are equal to one another. And that is what the power law says. Okay, you could just take the most basic function, which in this case would be f of x, or maybe g of x, is equal to x, and work with that limit, okay, and square it. Now, the root law is very similar to the power law because remember, a root can be written as a rational exponent. So like a square root is what power? So like a root and a rational exponent. Yeah, so 1 over 2, right? A half is the exponent, or a cube root a third is the rational exponent. So that's why these are so closely related. It's just because of whatever that exponent is. It just happens to be a fraction. Okay? Any questions? Okay. Well, what we're going to do is to use these limit laws to find a limit of a polynomial. We're going to do this in expanded form, which means many steps. And then we'll do it hopefully in a simpler version, and it'll be a lot nicer. Okay, but use the limit laws to evaluate this given limit. The limit of 4x cubed minus 7x squared plus 5x minus 9 as x approaches 3. Okay, so think about wanting to split up these terms into the most simplest of expressions. So when I go back to the limit laws, I'm going back to the first two that we looked at that aren't on this paper. The limit of a constant and just the limit of x, right? Y equals x. Okay, so that's our goal. Try to get it in those forms if possible. So to do that, we're first going to use the sum or difference laws. Because we're going to break this up into the limits of multiple functions, not just one. So it'll look like this. Equals the limit of 4x cubed, okay, as x approaches 3, minus the limit of 7x squared, okay, as x approaches 3, plus the limit of 5x as x approaches 3, minus the limit of 9 as x approaches 3. Okay. Well, that last term that we have, that last limit, is in one of those forms. So I don't have to do any more simplifying for it currently. But I am going to still work with these first three. So the next, what about those coefficients? The coefficients of x, can they not be factored out, right, using the constant multiple law? And so this becomes 4 times the limit of x cubed minus 7 times the limit of x squared plus 5 times the limit of x, and then just rewrite this last term. Okay. Maybe one other thing that we need to do is we want to get it down to just x, not x cubed or x squared. So what's another one of those rules we could do? The power rule, right? Okay, so we're going to take it, instead of the limit of x cubed, it's going to be the limit of x, in parentheses, cubed. So equals 4, parentheses, limit of x cubed. And then minus 7 times the limit of x squared. And then these other two will just remain the same. Okay, I think we're ready to evaluate. So this first one, the limit of x, as x approaches 3, we're going to kind of work from the inside out. That we just get 3, right? The limit of x as x approaches 3 is 3. And then we cube it. Okay. And then we multiply by 4. So I'll write it like this. This is 4 times 3, that was 3, cubed. 4 times 3 cubed right now, minus 7. The limit of x again is 3. 3 squared, okay, plus 5 times 3 minus, but this last one, the limit of 9 is what? 9, it is, as x approaches 3. But it could be as x approaches any number. It's still going to be 9. And now we evaluate, and that'll be our answer. Okay, so 4 times 27 minus 7 times 9 plus 5 times 3 and minus 9. So maybe 51 altogether. Okay, well, so good news, you know, this is not necessary all the time, but it shows you how these properties are at play, that they are definitely necessary. It's kind of like we don't think about all our properties of algebra, you know, regular, we just do them, you know, commutative, associative, distributive, we just do them. But we still need them, right, in order for us to say that this math is true and correct. Okay, so all together, here it is. The limits of polynomial functions are function values, so that helps this out. So this first one just says if p of x is a polynomial, and q of x is a polynomial too. So p of x and q of x are polynomials. Let a be a real number. And then what we can say is the limit of p of x, this polynomial function, as x approaches a is equal to p of a. That's the function evaluated at a. I was going to try to make this a little bit bigger, but this is the same example that we just looked at. And it's the limit of 4x cubed minus 7x squared plus 5x minus 9, a polynomial. Okay, because we know this rule, we can just use direct substitution. So it's 4 times 3 cubed minus 7 times 3 squared plus 5 times 3 minus 9. That looks like my last step in that last example. Okay, and all together, we totaled that to just be 51. However, if we do have a rational function, now this is such, like when we saw earlier, I think it was like x minus 3 over x minus 1, something like that. If it is such that q of a doesn't equal 0, so when you substitute in and you try to evaluate it directly, that you don't get a 0 in the denominator, then you can actually use those function values. It's p of a over q of a. It's the numerator evaluated at a, and the denominator evaluated at a, is what this says. And so what this would show for this particular function, the limit of 4x cubed minus 7x squared minus 5x minus 9 over x minus 1, as x approaches 3, is the same thing as 4 times 3 cubed minus 7 times 3 squared plus 5 times 3 minus 9. We already know what that is, but I'm showing you I'm just evaluating the numerator. at 3. And the denominator, 3 minus 1. So altogether, we get 51 halves, 51 over 2. Okay, so there are times when we arrive at indeterminate form. And we saw one of these earlier. Oh, oops, that was not what I meant. We saw one of these earlier that had a limit. The limit existed, yet we couldn't evaluate it as quickly. And so here's a few examples of where that might be true. Here are some rational functions, okay, whose limit appears to not exist at first. Okay, so this first one, the limit of x squared minus 4 over x squared plus x minus 6 as x approaches 2. Okay, so I think that this may even be one we had earlier. 2 squared minus 4 is 0. 2 squared plus 2 minus 6 is 0. 0 over 0 is called indeterminate form. And we have to do a little bit more investigating. But what I know I can do with some polynomials is to factor them. So what we're going to try to do is to find an equivalent function that's equivalent in almost every place, okay, except at x equals 2. And to do that, we simplify. So this is equal to the limit of x. This is a difference of 2 squares. So x minus 2, x plus 2 over. And then in the denominator, we're trying to factor x squared plus x minus 6. So what is that? X minus 2x plus 3. Good? Okay. So their product is negative 6, but their sum, negative 2 and 3, is 1. And now I can simplify. Okay, so look at that. What we are now saying is that the limit of the original function is going to have the same limit as this new function that we found. These functions are not the same, but they will have the same limit as x approaches 2, if that makes sense. Okay, but let's see what happens. So the limit of x plus 2 over x plus 3 as x approaches 2. We'll talk about this soon, but when I canceled those factors out, you probably remember this from pre-calculus. When I canceled that out, it told me I had a certain kind of discontinuity to the graph. You remember what it is?
I know what you mean.
Yeah, that this type here will be that missing point. It's a removable discontinuity. So now what we're doing is going to have a graph that doesn't have that missing point, right? It's continuous at x equals 2. And then maybe I can figure out what that answer is. So now let's try direct substitution. Okay, so that's 2 plus 2 over 2 plus 3, or 4/5. which I think we found 0.8 earlier. Remember that? 0.8? Okay. This next one, the limit of x as x approaches negative 3 of the square root of x plus 4 minus 1 over x plus 3. Okay, so upon using direct substitution, okay, and I see that'd be square root of negative 3 plus 4, square root of 1, 1, minus 1, so 0 over 0. Okay, so just do a little check. If that happens, don't stop, don't give up. I'm going to continue, but I'm going to do some kind of algebraic manipulation. It's semi-like when we are trying to simplify radicals in like algebra, that sometimes I want to multiply by a conjugate binomial. There are times when I want to multiply by something with a conjugate. And I think that's probably what I'm going to try here. It's also kind of similar to simplifying non-real numbers, like your complex numbers that have I in them. You know, sometimes we have to multiply by like 2 minus I, right? So instead of 2 plus I want 2 minus I, and then we simplify, and it ends up working out a lot nicer. That's, I think, the idea that we're going to do here. So I'm going to use a piece of paper, scratch paper, and all I'm going to do for a second is just to work with this. For minus 1 over x, okay, sorry, I forgot what it was, x plus 3. Okay, so here's my work on the side. I'm just going to do some scratch work. We're going to multiply by maybe the conjugate of this. Okay, so what changes, the only thing that changes is this sign in the middle. So we'd multiply by the square root of x plus 4 plus 1. And then the square root of x plus 4 plus 1 in both the numerator and denominator. Okay. That way it doesn't change the value of the expression. I don't want to do that. I just want to change how it looks. Okay. Now, FOIL, okay, or distribute. So in the numerator, I'm multiplying this and this together. And then in the denominator, I'm multiplying those. But I don't know if I'm going to, I'll have to see about what I'm going to do with those in just a second. But right now, let's do the numerator. The square root of x plus 4 times itself is just x plus 4. Okay, so x plus 4. But look at that. The outer and the inner conjugates are so nice because their middle terms just cancel out, which is why it's helpful to use it. So now I just have to multiply negative 1 by 1. So minus 1 over, and maybe don't distribute in the denominator. You see that? I'm not distributing for a reason. X plus 3 times square root of x plus 4 plus 1. And now I see this is x plus 3. X plus 4 minus 1 is x plus 3. The denominator has a factor of x plus 3. And so really, if this is okay, can I just do that now? Okay. And we get is equivalent to 1 over the square root of x plus 4 and then plus 1. This is what I'm going to pull back in. I'm going to take the limit of this function as x approaches, was it negative 3? Okay. And now we can use direct substitution. So that's 1 over the square root of negative 3 plus 4 plus 1. So 1 over the square root of 1, so 1 plus 1. So just 1/2 altogether. Okay. Any questions? Okay, what about this next one? The limit of 1 over x minus 1/2 over x minus 2 as x approaches 2. Okay, so I'm going to do a little bit of scratch work just with this expression. 1 over x minus 1/2 over x minus 2. I think that was it. That's right, because it was as x approaches 2. Is that right? As x approaches 2. So we get 0 over 0. And I say, I want to say does not exist, but I shouldn't say that. Okay. Is there a way to rewrite this expression, to transform it? What do you think? Any ideas?
Well, the half that you can go to denominator, maybe?
So that 1/2 in the numerator?
Yeah, I can go to denominator. Like 2.
Mm-hmm. So I think what you're thinking, if this were only a 1/2 right there, then yes, definitely you could put it with the 2 and then have it, but it'd still be distributing to both of those terms. It's a little bit more complicated when we have these two fractions with a sum or difference between them.
Yeah.
Okay? Any other ideas?
So keep changing it.
Okay, so you want to multiply by 1 over x minus 2. What do you think? Is that what you're trying to do? Or no? Tell me what.
I guess I was just thinking we keep 1 over x minus 1/2.
Okay.
Change the division
Mhm.
and then multiply by x minus 2 over 1.
But I think it would still be 1 over x minus 2 when you did that. Let's see. So you would say 1 over x minus 1/2. Okay, so that's keeping it, right? Changing the division to multiplication, so times, I'm going to put parentheses here, the reciprocal of this. So 1 over x minus 2. And let's see. I definitely think this is definitely a possibility. Okay, let's see if it gets us anywhere, because I'd still need to distribute, right, this fraction to each of these. Okay, so it's 1 over x, the denominators get multiplied together. Okay, are we getting anything better? I don't know. The only reason, I may stop, but I don't know. The only reason is to then still plug a 2 in, and you see we still have a 0 in the denominator, do we not? Okay, still an issue, but that's a good idea. You know, that's definitely a valid type of arithmetic. Okay, so that's definitely possible, but I'm just going to give you an idea, and you can say yay or nay. Hey, I don't know how far I have gone with this. You could definitely use a conjugate if you would like. I don't know how far it will take us, but I do know there is an option to try to get rid of the fractions in the numerator. That's what I'm going to do. Okay, so try to get rid of the fractions in the numerator. Now, how to do that is to multiply by the least common denominator, okay, or the least common multiple of those denominators, the x and the 2, which is just 2x. Okay, how nice is that? So we're going to multiply the numerator by 2x, but don't forget you have to multiply the denominator by 2x as well. And now let's distribute and see if it works out a little bit nicer. So that's equal to 2x times 1 over x, the x's cancel and we still have a 2. And then 2x times 1/2, the 2's cancel, and we still have an x. And so altogether we get, I say 2 minus x in the numerator over, okay, leave this as these factors, 2x times x minus 2. We're getting somewhere because 2 minus x and x minus 2, it's like 3 minus 4 and 4 minus 3. Those are just opposites of one another, are they not? So I can rewrite them so they look the same. And I could do that just by factoring out a -1 in the numerator. Okay? So equals negative x minus 2. Okay, so now that looks identical to that factor in the denominator, but it's really negative x plus 2, or 2 minus x, which is the same. Those two are equal to one another, those two numerators. So 2x times x minus 2, and now cancel. So all of that work shows us that we have an equivalent, for the most part, function of -1 over 2x that we're going to find the limit of. Okay, so let's pull that back in. We'll say that this is the same as the limit of -1 over 2x as x approaches 2. And now I can easily evaluate this. -1 over 2 times 2, or -1/4. Okay, well, we've talked about a lot of stuff today. Let me see. I want to make sure I have not forgotten anything. Any questions just so far on how to do some of this? I mean, they're algebraically not complicated, but you kind of have to have an idea of how to start it, right? So if you see something with a radical, maybe try using the conjugate. If you see something with fractions within fractions, try to get rid of some of the fractions, okay, and see if that leads you somewhere. And so we talked about limits that don't exist. Let's briefly look at this example to see if this limit exists at x equals 0. If you take a look at this graph, what it would kind of look like. We have a curve, a quadratic, -x squared minus 2, and then we have this line, and they come together to form this piecewise defined function. Okay, so without getting into details, okay, negative minus 2, it could maybe do something like this. So we have the quadratic on the left of 0, hopefully, and then on the right of 0, we have this line. Okay, not to scale, but does everybody see how that could be very similar to what this equation shows? Okay. Well, hopefully I'm right. But anyway, when these come together, though, look around 0, like that when you were looking at that last homework problem, where you still need to look at both the left and the right-hand pieces of this piecewise defined function to get the answer. You still need to look on both sides, right, of 0. But what are we going to say? What is the limit of the function as x approaches 0? Okay, well, do these match? So from the left-hand side, from the right-hand side, they don't match, do they? So we're going to say the limit does not exist. Do I have to graph to see this? This is another thing where you could try to evaluate the function for the different pieces at 0. And what you want to see, I mean, it really helps if our piecewise function comes together. How nice would that be? Because if the pieces come together, the function value is going to be equivalent to whatever the limit is. Okay? They don't have to come together, as in this case, but then our limit does not exist. Okay? Any questions? Okay, well, thank you all so much for coming, and I hope, you have a good amount of information to get you started on those 2 sections. If you do have any questions before next class, just let me know, but we're going to meet, unless something crazy happens, we're going to meet both days during the week because your class is under 10. Okay? Okay, I'll see you on Wednesday. Bye, guys.
Thank you.
You're welcome.